Okay, picking up where we were last time, we were talking about this idea of parametrizing surfaces, and just a reminder of the big picture. Where we're going with all of this is we're going to try to take all the ideas that we did for two-dimensional, XY plane, right? Two-dimensional vector calculus. We're going to try to come up with kind of analogous ideas. It worked out so well in 2 dimensions. What are the analogous ideas in 3 dimensions? And so, of course, if you're in 3 dimensions, you're naturally going to be interested in surfaces. Parametrizing surfaces is a good first step. So, reminders. Let's see here. Yeah, so we have this idea of a parameterization. And if you have a little piece of area over here in the domain, it's described by what you might call edges, like so. Now those are vectors, but because it's a rectangle, we don't really need to view them as vectors. We can just think about the width and the height, ds and dt. Then correspondingly, there are images of those vectors, which are like this. And they are computed by way of thinking about the derivative. Oh, let's see here. Oh, what color to choose? I'll use orange. The derivatives of the parameterization. The 2 different partial derivatives are velocities of coordinate curves, and so effectively they're just tangent vectors pointing which way the parameterization is going as you vary individual parameters. And of course, if you go with velocity rs, and if the input changes ds, then the output changes rs ds, which is that little vector, that little edge vector. So using these, we can then talk about what this output area is, and the ratio between the output area and the input area is the stretching factor. And we talked about that last time. The stretching factor, the amount that this area gets stretched out by the parameterization, is the magnitude of the capital N vector. Okay, what's the capital N vector? The capital N vector, as it turns out, now of course we did the calculation, thinking about the magnitude of the cross product of those 2 little edge vectors and go and do a little bit of algebra. We found this capital N vector is just the cross product of those 2 partials. It's RS cross RT. Okay, so these are the major players, and this is about where we left it last time. So I'm going to make the observation that we can kind of take it just a little farther. Not that you have to particularly, but I mean, R is position. It does have coordinates X, Y, and Z. So when you take the partial with respect to S of R, you're taking the partials of those coordinates, and so you can just rewrite that in coordinates, like so. And then likewise for the other partial. Okay. Here's another thing you can do. We know how to do cross products when we have the coordinates, and you can take this expression and crank it out. And here's what you get. And this is the I'm going to call it an unexpected result. Weirdly, the coordinates of that cross product, the coordinates of your capital N vector, end up being 2-dimensional change of variables stretching factors. Isn't that weird? Right? Unexpected. To say we're not doing a 2-dimensional change of variables, right? We're parametrizing a surface. We're in 3 dimensions. Where did a 2-dimensional change of variable stretching factor come from? Right? Valid, concern. There's a great reason for this, as it turns out. And tragically, it doesn't make the cut for what we have time to talk about in this course. So, I'm not going to tell you. Unless you come to office hours, if you're curious, if you would like to see why 2-dimensional change of variables stretching factors show up here, there is a very natural geometric explanation. And again, I'd be happy to show anyone who wants to hang out after and discuss. Okay, but anyway, for the moment, let me just kind of drop that point, that quick thought there. Okay. All right. So here is a variation of this. Oh, by the way, I should note again, summarizing. Here's where we ended last time. We ended with actually using this stretching factor to compute an area, right? So we computed the area of the unit sphere We looked at little output pieces of area. We recognized them as being stretched out results applied to input little pieces of area, right? Just like we have it set up on the other page there. And we computed the stretching factor. Now that was an ordeal, right? To figure out what that stretching factor is. That the stretching factor is just sine phi, as it turns out. And again, y'all are going to go through and confirm that algebra. Again, it's a healthy exercise. We're going to make sure that you can do that comfortably. Right? And yes, you do have to use the Pythagorean identity several times. I think it's 3 times if I remember right. But it's ultimately just a computation. It's just algebra and some trig. Okay. All right. So here is a twist on that. Kind of a neat little special case. I mean, we have a formula for what to do when we have a parameterization. But we also have a favorite kind of parameterization. At least that's my personal favorite. What I like to call the graph parameterization. And to be more clear, a rectangular graph. Right? So so the special case we're considering here is just where one of the rectangular variables, I'm going to use z, typically what we do, is solved for and written as a function of the other 2 rectangular variables. Emphasis on rectangular. Got to be rectangular. Okay, so here's how it works out, and it's just neat that you can just carry this through, and it is what it is. But the graph parameterization is exactly that, right? That's the rule. You let your input variables, right, be your parameters. So I'm just following the rules of what the graph parameterization is. Now I got to take the partials of that. Well, yeah, if you take the partials, you're gonna get little 1s and 0s exactly right there every time. Because, well, look at it. I mean, the parameterization has this very strict structure where we put the s and the t right there. Okay. Then when I take the cross product. When you take that wrong color. You take the cross product to get the capital N vector, it's going to be this every time. It'll always be exactly of that form every time. Again, just look at the structure. That's multiply it out. That's what it is. And then when you take the magnitude, you're going to get that every time. And of course, that magnitude is our stretching factor. So you can just memorize this formula. I think it's a great choice. Memorize this formula, and that means anytime you are using a graph parameterization, you don't even have to go through the multi-step process of taking the partials and doing the cross product and computing the magnitude. This has already done that for you. Very handy. Right? Now, asterisk. Important asterisk. This only works if, big if, right? You gotta be super careful with this. You are using specifically the graph parameterization, and again, I emphasize rectangular graph parameterization. I am not saying that this is an acceptable alternative to the general formula, right? The general formula that N is computed by that formula, and the stretching factor is the magnitude of capital N. That's the general formula. You will experience situations where a graph parameterization will not work. Specifically, a rectangular graph parameterization doesn't work. Right? The surface is not suited for that for whatever reason. So you have to know the general formula. This special case is a handy, alternative for those times in which you do use a rectangular graph parameterization. Okay. All right. Okay, by the way, while we're at it, let's just notice that these 2 terms together are exactly magnitude squared of the gradient of that function little f. And keep in mind, we've got this function little f. That tells me how z is a function of x and y. It has 2 input variables, x and y. Therefore, the gradient has 2 partials, and boom, there you go. That's what that magnitude is. Now, having made that observation, here's another lucky break. The magnitude of the gradient tells you how steep that graph is. It's just steep. Now, if you were standing on that graph, like that graph is a hill, how steep is it? That's what the magnitude of the gradient tells us. So, beautiful little fact, not only in this, and again, emphasize, in this special case, not only is the stretching factor a pat formula, but it's very naturally connected to something that's geometrically obvious. Right? I mean, how steep a surface is just, that's a very geometrically natural thing. Okay, so let me show you a cool application. By the way, this is a very real application, and this is something that I encourage everyone to do when you, if and when you ever get to the point where you're a homeowner and time to put a new roof on the house. And by the way, you don't get lucky with some sort of, we had hail damage and the insurance pays for it. I got lucky that way myself. But if you have to actually pay for your own new roof, it's many thousands of dollars. It's bonkers expensive. I was not prepared for the size of, and we're talking 5 digits. Expensive, right? Very, very expensive to put a roof on a house. Depends very much on the area of your roof. Wouldn't it be nice if we can compute then the area of our roof, right? The roofing company's going to come over and some guy's going to just say, yeah, here's the area of your roof, and we got to buy the blah blah and the labor, etc. And so this is how much your roof's going to cost. You want to check? I encourage anyway. Do whatever you want. I encourage you to check and make sure that they did not accidentally miscompute the area by, let's say 10%, something easily unnoticed, perhaps. That might still cost you $1,000 or $2, right? A couple grand is worth a quick calculation. So here's the cool observation. And by the way, this is not a fact of physics. This is just a tendency in architecture. Roof steepnesses tend to be constant over the entire roof. There are exceptions, of course. This is, again, not any sort of law, set in stone or anything. But it just tends to be many houses, most houses. I don't want to overstate it, but certainly many houses have this feature. So if you go up into the attic and if you measure, how steep is it there, rise over the run, and then you do the same thing over here, rise over the run, same number, same steepness. Okay, so what? What does this matter? If we're going to compute the area of this roof, one would think I'm going to have to compute the area of that triangle, and then I'm going to have to compute the area of that parallelogram, I guess, and then I'm going to have to compute that. And by the way, how am I going to compute those things? Am I going to have to get up onto the roof and measure, for example, that distance? It depends on your house, I suppose, but I do not have any desire to get up on top of my roof. It's really high up there, and it's concrete underneath, and I'm scared of falling, right? So I'm not doing it. I'm out. Forget about it. Okay. Not only would you have to measure the lengths, did you have to measure angles and stuff like this. You'd have to measure that angle so you know how to use these lengths to compute that area. Blah, blah, blah. Bunch of super inconvenient stuff. So here's the alternative. Right? You don't have to do any of that. That's the beautiful thing. You don't have to do any of this. You recognize that even though it's made up of a bunch of different faces, the roof is in fact a graph. Right? Over any point on the footprint of the house, there is exactly one point on the roof directly above that. So it's a graph. Not only is it a graph, but it's a graph where, as we just discussed, the steepness is constant. And if the steepness is constant, that means that your area stretching factor, that whole area stretching factor, is constant. everywhere on the roof. And so this makes for a fabulously convenient computation. And all you got to do is, again, just realize that each little piece of area on the roof is sitting over some little piece of area in the footprint. And the area of that piece of the roof relates to the area of that piece of the footprint by way of the stretching factor, which we have just established is constant, thus leaving me, you'll notice, now only with adding up a bunch of little pieces of area of the footprint. In other words, it leaves me just to compute the area of the footprint, and that's a super easy calculation. Anybody can do that. You don't have to climb on anything. You just get a tape measure. You go around the perimeter of your house and draw a little picture, and that's just a couple of rectangles. You can add up the areas of a couple of rectangles very easily, right? So, nice fact. Very convenient thing to do. And by the way, how do you know what that steepness is? Well, that steepness is something you can literally go up and measure in the attic, right? You can just basically look at a little triangle like that, drop a string with a mass on the end of it to get a vertical, right? Measure the horizontal. No big deal. Easy to do. And computation done. What do you think? Everybody see that? It's a neat little calculation. I encourage everybody to be prepared to do that in a few years, again, whenever you have to put a roof on a house. And moving along. Okay, let's see here. Where am I? Okay, moving along. Okay, so that finishes 7.1. Moving on to 7.2. We're going to talk about surface integrals. Let me remind you, why are we going to talk about surface integrals? Well, with optimism, because we remember that in 2 dimensions, line integrals ended up being interesting, right? They were useful for various different things. And so doing an integral on a surface is kind of a 1-dimension higher version of that. I'm going to point... While we go here, oh gosh, that's not what I meant to do, sorry. There we go. I'm going to point out that, okay, I don't know why that's doing that. There we go. Okay, I'm going to point out, you can see the way this is laid out on the pages. On the left, we have the process we're about to go through to define surface integrals. On the right, back in chapter 6, when we started to define line integrals, and I have deliberately, as obviously as I know how to do, made these arguments, these calculations, these choices, explorations that we're doing. I've laid them out on the page as analogous as I can, reasonably, right? And they are strongly analogous. Back in chapter 6, we had a curve. And look, we chopped it up into little pieces and then argue that if you have some accumulating quantity, the whole is the sum of the parts, and I've now chopped it up into parts. And we'll just add it up over all the parts. We're going to do the same thing for surface integrals. Same basic idea. Whoa. There we go. Same basic idea. We've got a surface here. And maybe I've got some accumulating quantity distributed over the surface. For example, maybe that surface is the surface of a hill, and there's a bunch of grass and such growing on the hill, and I would like to have some way to measure how many blades of grass there are in that hill. And by the way, it's complicated by the fact that at the higher, up near the top of the hill, the grass doesn't grow as well up there. Maybe it's because there's less water, or, whatever. And then down at the bottom, the grass grows a lot better. So the grass density, blades per unit area of grass is lower at the top of the hill, higher at the bottom of the hill. How do you add up all those blades of grass without, getting out there with a magnifying glass, and a clicker, right, and actually measuring them all? So, big idea is number of blades of grass is an accumulating quantity. The whole is the sum of the parts. And so look, on any individual piece, I can talk about number of blades per unit area times area. Right? So this, what I'm calling a density, right there, that's stuff per unit size, which you see then I'm subsequently multiplying by size. Right? It's our classic notion of a density, stuff per unit size, which is to be multiplied by size. And that gives me stuff, that gives me the number of blades of grass on that little piece of area. And then if I want to add up over the entire surface, okay, well, sure, let's add that up over the entire surface. That's all that summation is. Limit, of course, to make these pieces smaller and smaller so round-off errors go away. And this is another Riemann sum. It's a brand new kind of Riemann sum. It's structurally, morally, the same idea as every other kind of integral we've ever written down. Just doing it on a surface instead of on, an interval or on a two-dimensional area in the plane or a three-dimensional solid or what have you. Okay. All right. So with that idea in place, here's the notation that we're going to use to represent it. I think this is pretty believable notation. Again, we use a double integral symbol to represent that we're adding up over areas. ds as a sort of integral shorthand for delta s, representing the area of a little piece of our surface. And then, of course, don't forget to write down your integrand, namely your density. Oh, and then as usual, notice the domain itself is a subscript there for the integral symbol. Okay, so pretty believable notation. Now, again, just for emphasis, notice how it's a ripoff, right? It's a copycat of how we wrote scalar line integral notation. Really, really similar. Okay. All right. Thus the term, by the way, scalar surface integral. Okay. Let me pause real quick, see if anybody's got any questions. Anybody have any questions about this strategy? Again, we don't know how to compute these things yet. We'll figure out how to compute them in a second. But just this idea, the big picture strategy of we're going to take a surface, chop it up into little pieces, the whole is the sum of the parts, etc. Everybody on board? Okay, moving along. Okay, so how are we going to compute this? And the good news is we actually already have all of the tools that we need. In fact, we've already kind of computed an integral on surfaces. Back here, last time, this calculation here, where we computed the area of the unit sphere, right? I kind of waved my hands at this earlier. So this calculation, literally, I was adding up over the sphere. And how did I do it? Well, I pulled back through the parameterization and said, stuff I'm adding up on the sphere, I'm instead going to add it up on the pullback space, in this case, the phi theta plane. So that's what we did there, and we're going to do morally equivalent thing now. Oh, whoops, that moved me the wrong way. Morally equivalent thing, we're just going to kind of keep it general here. Suppose you have a parameterization, any sort of a parameterization of a surface, right? And if you want to do an integral on that surface, again, we're just going to pull back through the parameterization. Everything that happens on that surface is an image of something that I can represent in terms of my parameters S and T. In other words, I can plug in, and don't forget your stretching factor, right? So our classic pullback concept, and that's going to turn the integral on that surface into an integral on some region in the ST plane. Again, just don't forget to insert your stretching factor. Everything else is just a matter of plugging in. Good news, we've already computed the stretching factor. Let's see here. Let me get my arrows straight here. My stretching factor that turns that area into that area, we've already computed. That's, the same stretching factor we already computed, and don't forget to put it on in there, and we win. This is how we compute scalar surface integrals. Pull back through the parameterization. Don't forget your stretching factor. Example to follow. What do you think about this strategy, though? Does everybody buy it? Okay. Alrighty. Okay, here we go. Oh, you know what? I always forget that I need to make this comment. This, again, we have the same concern that this is intrinsic to the surface. This does not know anything about a parameterization we might have chosen when we compute this. Our answer better not depend on the parameterization because the question has never heard of the parameterization. Wait a minute. My answer here seems to depend on the parameterization. The parameterization's in the formula. By the way, it's also in the capital N. Right? Don't forget the capital N comes from the parameterization. So, wait a minute, does this depend on the parameterization? That it shouldn't. It doesn't make any sense. How could it? And the answer is, mysteriously, when you work this out, the parameterization doesn't matter. So parameterize however you like. This integral, our pullback integral here, is independent of the parameterization. Very relieving fact, right? That better be true. Otherwise it would be obvious nonsense. Okay, alright, so now that with that out of the way, let's do one. By the way, I am again deliberately following the pattern of what we did when we were talking about scalar line integrals. Starting with a scenario. We are over here, again, going to start with a scenario where we ask several questions: mass, center of mass, moment of inertia. So likewise, let's compute mass, center of mass, moment of inertia. Right now, just over a surface instead of over a curve. Okay. And again, the calculations are going to be pretty analogous to each other. After all, they're all over the same surface. Therefore, they're all using the same parameterization, or we may. The parameterization will therefore give us the same stretching factor, the same bounds, the same everything. It's just a question of how do we apply them to different integrals. Okay, so here we go. Let's get that stretching factor computed. We are starting with the upper unit hemisphere. This is a fabulous way to parameterize any part of a sphere, really. You just gotta, we are going to have to think in a bit about, okay, what are the corresponding values of phi and theta? They give us specifically, not the whole sphere, just the upper hemisphere. Right, and we'll get to that in a bit. But that's an old parameterization of spheres, and yada yada yada. Right now, this calculation here is something that, again, everybody should check, but you should in fact already have checked this. This is the exact same parameterization of the sphere that we did recently, right? That we did when we were computing the surface area of the sphere. So same calculation, and we already know the punchline, and that is the stretching factor is sine phi. Okay. Good fact to remember, by the way. Okay, and so with that said, let's see here. Let me squeeze down so I can fit it all on. And starting with computing the mass. Well, the whole is the sum of the parts. Any given little piece of mass is mass per unit area times area. Mass per unit area is given. Notice all I'm doing is plugging in. Right? This is a follow your nose computation. It's kind of sort of always the same. ds is stretching factor times parameter differentials. So ds is capital N times d phi d theta in this case. By the way, notice on the right hand side, all those same things still apply. Let's see here, colors. Totally analogous calculations. Yeah, sure. the x-coordinate of the center of mass is computed by a different integral, but that integral is made up of a lot of the same players, and those players simplify in exactly the same ways. So you can think of these as kind of parallel computations. Okay, et cetera, et cetera. Oh, now one easy one to forget, very easy to forget. What do I do with, oh gosh, color choices. I'll use dark green. What do I do with Z? Right, where does Z come from? Don't forget, Z is a position, Z is an output coordinate, and output coordinates, right, in this case, Z, output coordinates are part of the parameterization. Z is literally the third coordinate of your parameterization. And we have already chosen a parameterization, so Z being that third coordinate, Z is that. Right there. And so, boom, we plug that in like so. Everybody good? See how this calculation plays out? Okay. All right. Okay, let's see. Last detail. We made reference to this, and now we got to actually do it. Last little matter is, how do I specifically indicate with this integral that I'm looking for the upper unit hemisphere, just the top half of the unit sphere, right? Not the bottom half. No bottom. Just the top half. Right? So, how is that reflected in this integral? Well, if you think about it, even if it's the top half, it does still go all the way around in the theta direction, right? So, theta goes from 0 to 2 pi, and notice, let's see here, I'd better zoom, oh come on, there we go. Notice we have theta 0 to 2 pi. Right? And then, now again, thinking about just the top half of the sphere, phi, that starts at 0 going straight up, phi just goes down to the equator, where phi is pi over 2. And so phi goes from 0 to pi over 2. So that's how we indicate the top half of the unit sphere. How are we doing? That make sense to everybody? Okay. All right. Cool. Again, many more details. I'm going to leave the rest of the details for you all to think through. What we have on the right is more of, it's a different integral, but the computation is the same process, just a matter of plugging in. And then I think it's a nice exercise, let y'all read this on your own, but to think through further details, such as what if you want to compute that moment of inertia, and you got to remember the formula for moment of inertia, but basically the same ideas. And again, you notice the patterns, right? ds is still stretching factor times d phi d theta, etc. Okay. All right. Good reads. Okay. Next thing. Y'all remember flux. This is flashing back to chapter 3. Right? We computed this thing called flux. Y'all probably recall we drew a picture that looks like this. That picture is of the parallelepiped's worth of fluid that flows through my area in any given little short period of time. Right? And we computed that volume and did a little bit of vector analysis, and ended up with the punchline that the flux is computed by this formula. Now, what does that mean physically? Well, it means a couple of different things, depending on what you mean by a vector field representing a fluid. If your vector field representing the fluid is giving you velocity of the fluid, then flux is telling you volume per unit time of fluid passing through your surface. On the other hand, if your vector field is density times velocity, this was a suggested calculation I encourage y'all to do back in chapter 3. Excuse me. In that case, flux gives you not volume, but mass per unit time passing through your surface. Okay, so neat thing, flux is a really natural thing to talk about. It has natural physical interpretations, and you can have either one of these interpretations you want. Just make sure that you set up your vector field appropriately to get that. Okay. All right, now, bad news. You may have noticed this at the time. This only works if your area is flat. And it furthermore assumes that the vector field is constant. Right? That's, I wouldn't have a parallelepiped if either one of those went wrong. The whole calculation we did back in chapter 3 was based on that being a parallelepiped. So again, constant vector field, flat piece of area were unavoidably assumed at that time. Okay, so what we want to consider now is what if F is not constant? What if the vector field changes? What if the vector field, varies over the surface? Which, by the way, real world, right? Very often, usually, vector fields are not constant. Right? And then likewise, what if your surface is curved, not flat? Well, there's a lot of flat surfaces in the world, and that's nice and everything, but there's a lot of surfaces that are not flat. So we want to be able to deal with them as well. By the way, let me flash back again. I didn't mean to do that. Flashing back again, back into chapter 6. You may recall, we entertained the idea of an old formula that made assumptions about a constant vector field and a flat piece of curve. Here, we have an old formula that's computed based on a constant vector field and a flat piece of area. Very similar. Eyebrow raiser, right? It looks highly analogous in certain ways anyway. So just for your consideration, what did we do in the case of the curve? Well, what we did is we said we're going to take this whole curve and we're going to chop it up into little pieces, because on each little piece it's approximately straight. And the vector field doesn't have much of an opportunity to change over such a short distance, so the vector field is approximately constant. So the act of chopping up that curve into little pieces gives us our two nice assumptions. And we're going to do the exact same thing over here now. We're going to say, look, I'm going to take my non-flat surface, and I'm going to take my non-constant vector field, and I'm going to chop it up into a bunch of little pieces. On each little piece, it's a teeny tiny itty bitty little piece. It's approximately flat. On that itty bitty teeny tiny little piece, there's just not that much room for the vector field to have time to change very much. And again, we're assuming nice regularity conditions on the vector field. Vector field has to be continuous. And so, approximately flat, approximately constant, and so we are now in a position, at least on that little piece, where we can use our old chapter 3 formula. Everybody good? Everybody see how we're kind of stealing chapter 6 ideas and just kind of adapting to this three-dimensional circumstance? Okay, now, it's weird, it keeps pressing before I press it. What else did we have to consider back in chapter 6? We had to worry about orientation. And this kind of snuck up on us. None of the previous computations we did with line integrals involved orientation. But very importantly, if you are moving along a curve, if you are computing work, you are very importantly going in a specific direction along the curve. We need to indicate, it's going to give you a different answer if you climb up the hill versus if you climb down the hill. Importantly different answer. So we distinguish between those with this thing called an orientation, which is just a way of indicating which direction along the curve am I going. Okay. Something very analogous is going to come up here. And that is, I've got to indicate which direction do I want to consider to be the positive direction through the surface. I mean, here I have it drawn like so. I'm going to say that, let's keep track of fluid flowing that way through the surface. If I were to, for whatever reason, if the fluid, let's say, were like this, notice the fluid is going through the surface, and it is going the same direction that normal vector is pointing. But if the fluid went the other way, that's a very different phenomenon. And I don't want to get the same answer, right? I want to have my formula recognize that fluid flowing the opposite direction is a significantly different thing, right? So we recognize that with the normal vector. The normal vector is our that's our notion of positivity. What's the positive direction through the surface? And this is called an orientation on the surface. And with that settled, we have what's called an oriented surface. An oriented surface just has an orientation. An orientation is just a choice of which direction does the unit normal vector point. Okay. All right, so just to be clear on the terminology, that normal vector is called the orientation unit normal. Normal because it's perpendicular, unit because it has magnitude 1, and orientation unit normal because this one specifically, not this one, right? But whichever one I've chosen specifically is what gives me, right? That choice of normal vector is what tells me what I'm calling the orientation on the surface. Okay. All right. Now, with that settled, it's all over but the shouting. On any given little piece of area, right, from chapter 3, we know that this is the amount of flux happening on that little piece of area, right? It's vector field dot normal vector times whatever is the area of that little piece of surface. Chapter 3, old news. And if I want to add that up over the entire surface, right, over the entire surface, adding up a bunch of little d phis gives us an expression that looks like this. How we doing? Everybody okay? All right. Okay, now, there's a temptation to look at this and say, okay, well, that's a scalar line, a scalar surface integral. That looks just like, it says integral, blah, 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 d capital S. That looks just like these scalar surface integrals that we computed previously. It looks just like the general construction we made for a scalar surface. Why is this not a scalar surface integral? And let me just remind you, these calculations here, when you compute the mass distributed over a surface, there is no notion of direction. There isn't, I was interested in computing this mass, but I want to look at it from underneath instead of on top or something, right? There is no notion of a direction for the mass. And likewise, the x-coordinate of the center of mass, it's wherever it is. There is no notion of orientation there either. And nor with any of the other things that we've computed with scalar surface integrals. So, somehow or another, this is a different critter. Somehow or another, this needs to depend on the orientation. And I'll tell you how I like to think about this. I like to think about integrals as having an integrand and a differential. But let's be careful and strategic and thoughtful about how we define what a differential is. And to me, a differential, and think back to Calc 1. Right, back to Calc 1. You've got your domain is an interval from A to B, and dx is a way of describing the little subintervals. Dx is what we need to know about little pieces of my domain. Likewise for every other differential we've ever written down. Well, here's the thing. Both N and ds are telling me about my little piece of the domain. ds is telling me the area. The N is telling me the orientation, which matters, right? It's an important aspect of that little piece of area, namely which direction is the correct direction to go through that little piece of area. So I think that makes loads of sense, and the notation that we use to kind of put these together to represent that this is in fact a single thing telling me about one single little piece of my surface. We call it the ds vector, and it's just little n times the ds scalar. Okay, so that's the vector surface differential, I'd call it. Okay, so now on the other hand, you can view this as just an alternative notation. Suit yourself. For whatever it's worth, a couple of selling points. This ds alternative, writing it like so, you gotta give it to me. It's a little bit more compact, writing it like that. That's kind of nice, right? I encourage it if only for that reason. But also, and I've made the following point before, this is a broad general point, when you have two things that are importantly, meaningfully different, it's good to be aware of that, right? And so we have here two different things. We have scalar surface integrals that have never heard of orientation, don't care about orientation. We're adding up a bunch of scalar quantities and there's no vector in sight. Versus this new kind of integral where orientation matters and which direction you're going through is important and is part of the deal. Those are different things. I think when you have different things, you want unambiguously different notations. And that's another nice thing about this notation here. It looks different, which it should. It looks different from a scalar surface integral. Okay, so I'm a big fan. I use this notation highly regularly. And anyway, enough of that. Okay, and good news. We already know how to compute these. We've already talked about parameterizations. We've already laid the groundwork. We've already computed all sorts of stuff. We've already got all of these tools. And so look how easy it is to compute this construction that we just wrote down. And that's nothing but a recopy. That's just literally copy-paste from above. This construction, if you just write down this right here, ds is magnitude of capital N times ds dt, like so, right? Then look what we end up with. Let's see here. Let's think this through. We have the magnitude of capital N. Okay. Then we have a normal vector perpendicular to the surface. Oh wait, capital N points perpendicular to the surface. So it's tempting, very tempting, and I'm not even 100% wrong to say, well look, this product, little n times the magnitude of capital N, it points in the same direction as capital N, perpendicular to the surface. It's got the same magnitude as capital N, right there looking at us. It looks like a duck and quacks like a duck. That makes it a duck. Right? So it's very, very tempting. Now, I did just commit a math crime, right? I'm deliberately being careful and sneaky with my language because I like to, for dramatic purposes, I do like to call this, get it wrong first, so that when we uncover what we did wrong, it'll be more impactful, and we'll do that next time as it's going to turn out. But pretty tempting just to say that's capital N. And again, I've committed a math crime. I will confess the crime next time. But notice what we end up with is a nice, compact, pullback formula for how to compute a flux pulling back through a parameterization. And again, we're just going to plug and chug with this formula right here. And we'll call it a day right there. We'll pick up with this example next time. Y'all have a good one. See you later. And see you Friday.